problem 4 on the problem set. We're basically going to rederive what we did in class, but from a Lagrangian perspective. So over here on the left, we have our inertial reference frame. We'll call inert S0. And then we have our non-inertial reference frame over here. We'll call non-inert. And so we want to find a way to compare how they observe this, say, just particle in between them. So what we first do is we draw a vector R naught going to here, which is what the inertial reference frame observes. And then we draw a vector from here to the particle, which is what the non-inertial reference frame observes. And then we draw the relative distance between them, which is big R, right there. And so in this problem, we're dealing with translational motion. So in reference to the inertial reference frame, this one is just sort of moving, I mean anywhere, but we'll just kind of say this arbitrary velocity v away from the inertial reference frame. So over here, we'll derive our potential. So we're given that the potential is just particles moving in some potential R naught. So
is this for just translational motion?
yeah, this is just translational.
Not rotational.
Not rotational, yes. And then the kinetic energy is going to be 1/2 m r double dot naught. And so in order to get that, if we look over here, we can recall that R naught is going to be equal to R plus big R. And then if we take the derivative, we get, oh no, sorry, excuse me, that's not double dot, that's one dot, because it's velocity dot.
Is it squared?
Acceleration. And yes, it is squared. So you get R naught vector, take the derivative, we've got R vector plus, then the derivative of this we're just given is to be v, the velocity that's moving in this direction. V of t. And then we want to square it. So R dot squared is equals this whole term squared. If you multiply it out, you get R dot squared plus 2 times R dot vector times the dot product. So note this is the dot product, we're dealing with vectors. Times the velocity plus the velocity squared. And I guess, is everyone good over here? Can I erase that, or should I erase this? Or
You go over here.
okay. All right. So we've got our. Basically, plug this into the R dot squared, and we can find our Lagrangian. So Lagrangian is going to be 1/2 m times R dot vector squared plus 2 R dot vector times V vector plus V vector squared minus the potential, and then just substituting in this R dot, this R naught into here, we get the potential is R vector plus big R vector.
Is there in your original R naught dot second equation there?
This one?
Sorry.
Yeah.
Is that supposed to be R with a dot above it? Or
Oh yes, you're right.
Okay.
The vector of the dots is just tons of things happening. It's hard to keep track of sometimes. And so yeah, that's our answer to part A essentially. It's just we need to set up the Lagrangian. And then from here we just do what we've always done, we take the Lagrangian of it, so dr, or partial of the Lagrangian to partial R is going to be the negative gradient of this, which is essentially the same thing as taking the derivative of the potential and the derivative of R. So it's just accounting for the gradient, just accounts for all the components in the x, y, z direction. And then d dt of dl over dr dot is going to be equal to m times r double dot plus v dot. So everyone kind of see where that comes from. Just this term, and then take the derivative and subtract the time, so I get the extra dot for each one above it. And so, over here, we get the result that m r double dot plus v dot is going to be equal to the negative gradient of potential of this r plus big R vector. And so one thing we know is that for definition, force is the negative gradient of the potential. Cool, so you can just plug that in. And if we multiply this out into its two components, we've got m r double dot plus m v dot equals F. And so we're told to sort of separate out the inertial force. So if you subtract over the mv over this side, you get m r double dot equals F minus mv dot. And cool. So essentially, this is all the external forces that are occurring on this particle, and this over here is our inertial force. This is what the, relative to the two reference frames, this is the inertial force we're going to observe. And so in that case, F inertial will be equal to negative m v dot, which is precisely what we found in class. I guess it was on Friday the 13th. So that's the answer to B. Are there any questions?